Hello and welcome back to Calculus 1, section 2.7 on definition of the limit. So, 1850, mathematician Weierstrass wrote down the concrete definition of the limit using what we today call epsilon delta approach. So, assume f of x is defined, so let's go red immediately. That's the definition. So we say assume f of x is defined for all x in some open interval. When I say some open interval, that could be negative infinity to positive infinity. That's open interval, right? Anything that has this form, that's open interval, and this is also open interval. So it could be from 1 to 3 or negative infinity to positive infinity. So we say just some open interval. Containing A. So A. So assume f of x is defined for all x in some open interval containing A, except possibly at A. This statement means that all of the values in the function have to be defined. They all have to have their y values, and the only open circle that you can have could be at A. Remember that limit still exists, right? If you have open circle, but that has to be a single open circle point in the neighborhood. So assume that f of x is defined for every y value and on open interval, right? Containing point A except possibly at A. All right. So we say limit x approaches A of f of x is equal to L if, and here is the core of the definition, if for every number epsilon larger than 0, there exists number delta larger than 0 such that absolute value of f of x minus L is less than epsilon whenever 0 less than x minus A less than delta. So this is the entire definition for the limit. We call it epsilon delta definition for obvious reasons. You have epsilon delta in it. And to make sense of this, we have to draw those pictures. Before we go and draw the pictures, the symbol is called epsilon. It's a Greek letter, and it is equivalent to our E. Delta is equivalent to our D. So epsilon, delta, those are Greek letters. You know other Greek letters. You know pi, you know theta, right? Maybe alpha, beta, gamma if you use those for angles. So you know, and you will see many more Greek letters as you go on. So here are the epsilon and delta, which are E and D technically. Now let's go and make the sense of this definition, and whatever I'm saying you can maybe summarize into the paragraphs if it shows up on a test you will be writing that stuff.
But the symbols on the definition is lowercase, uppercase matter.
Well, the epsilon is the lowercase because you have the uppercase for that, which is capital E, and over here you have delta, capital triangle, like that. So we are using the lowercase in this case, all right? Capital alpha is just like that, and then you have like each letter as their own. So can you give two?
Yeah, I'm
are you
7:12.
okay? So just give me 5 minutes and then okay. All right, so let's just go quickly through those two graphs, and then she's going to take over the class for a few minutes. So we have the graph over here. We have our function, f of x, and I'm going to pick my value a on x-axis, which is supposed to produce this limit L on the y-axis. Now, epsilon and delta are the small values around L and A. They're technically creating tubes around. So, you go, maybe I can use different color over here. A little bit to the left and a little bit to the right. This would be A minus delta and A plus delta, and each one of these is delta, which is the difference between A and the other 2 points. Now these will create the y values. These are terrible, so I have to fix them. And this is going to be L minus epsilon and L plus epsilon. The idea is, as you are making epsilons smaller, over here it squeezes to A, or if you're making delta smaller, you are getting a squeeze, which immediately gets a squeeze over there. Do we all see that? Right? I can't make that live, but hopefully you see that as you squeeze here, you are squeezing there, that will squeeze here, right? So that squeeze is actually making the limit. Here is your limit from the left, a squeeze happens. A limit from the right, the squeeze happens. It squeezes into this point, which squeezes into L, and we have our limit at L. So now you can see the squeezing, because the squeezing in that definition was portrayed by f of x minus L and x minus A, right? These points that are moving, those are x points. A is fixed. F of x is the moving point, and L is fixed. So as I am changing the difference between x and A, I'm squeezing x minus A, and I'm making the delta smaller. That means that the difference between them is reducing. This squeeze over here pushes into L. Bueno? There we go. That's the first graph. So the squeeze in delta produces the squeeze in epsilon produces a squeeze in delta. The limit at A is L. That's that. The second picture features our friend 1 over x. Limit does not exist. The squeeze in x is going to create the divergence of L. There will be no limit. So we draw we draw 1 over x on xy plane. I'm going to pick my a, which is 0. I'm going to go a little bit to the right, a little bit to the left, and that's going to bounce into y-axis. You have your delta, so this is your a minus delta, and this is your a plus delta. These locations, these points. Do you see that as you squeeze deltas, this over here is supposed to be L plus epsilon and L minus epsilon, right? Well, what happens as you squeeze? Let's go green. If you squeeze halfway, the new point is on top, and you squeeze halfway, the new point, you see that these two values are further away than where the previous ones were. They're not going to converge into a point. The more I squeeze on delta, the further away the two y values are. Are we agreeing on that? No limit. Because you can't have on one point two different values, right? That's why there's no limit. The squeeze on delta will make the infinite separation. In this example, it will make infinite separation of y values. So your left limit, the squeeze from the left, is producing negative infinity. The squeeze from the right is producing positive infinity. No limit, right? This is the graph for limit does not exist. And that's it. I hope you're not disappointed. You have the definition. You have the graph that explains that definition. Squeeze delta, squeezed epsilon, or squeeze epsilon, squeezes delta. That's when limit exists, and limit is L. So limit x goes to a of f of x is L. The bottom picture, limit does not exist. That's that. Bye.